Yes, thank you for the introduction. So first of all, I want to thank the organizer, especially Professor Payment, for the invitation to give a talk here. So today I will talk about arithmetic of generalized Fekete polynomials. So you can spend some time on some history of the problem. So why we came to the problems and so why interesting. So let me start the talk. So here's the plan of my talk. So first of all, I will talk about what it means to be a generalized Fekete polynomials. And then I will discuss some Galois theory for those polynomials, very exciting part. And then if time permits, I will talk about some applications in graph theories. So this is based on a joint work with Jan Minak and Nguyen. And so this is a continuation of our previous work, where we consider a special case where the discriminant is a prime numbers. And this previous work have been published in Journal of Number Theories, so accepted a few months ago. And this current work is submitted, but it's under reviews. So let me start with by recalling some basic information from number theories. So I will recall the Legendre symbol first. So the Legendre symbol we define in the following way. So we define the fraction of a over p, where this one is 0 if p is a divisor of a, it will be 1 if the a is square mod p, and it's -1 if a not a square mod b. So in other words, this Legendre symbols tell you whether a is square mod b or not. And then so there is also the Jacobi symbol, which generalize the Legendre symbol in a multiplicative way. So what it means is that if you factor b into a product of prime numbers like p1 to the power e1, p2 to the power e2, and pi to the power er, then the Jacobi symbol a over b is defined in the corresponding way. So you take the Legendre symbol with the appropriate powers. So in other words, the Jacobi symbol give a generalization of the Legendre symbol. But unlike the Legendre symbol, it cannot tell this. If this symbol is 1, it cannot tell a square mod b. Because you can imagine the situation where you have product of two prime numbers, and each Legendre symbol is -1. So when you multiply them, you 1. But a will not be a square. And then finally, there is something called the Kronecker symbol, which generalize both the Legendre symbol and the Jacobi symbol. So in order to define the Kronecker symbol, what we need to do is we define some additional rules. So we deal with the case where b could be negative. We add the rule that a over -1 is 1 if a bigger than 0, -1 if a less than 0. And then we have to deal with the prime number 2. So there's one more rule, a over 2 equal to 0 if a is even. It will be 1 if a plus or minus 1 mod 8 if -1 is otherwise. So here we can imagine that the Kronecker symbol is defined in a very similar manner. So a over n will be defined to be this product with corresponding to the factorization of n into prime powers. So this symbol here generalize both the Legendre symbol and the Jacobi symbols. And I will explain in a second why it matters for us. So we want to, so let's say d be a square-free integers. So delta will be the discriminant of the quadratic extension where you adjoin the square root of d to q. So we know that the discriminant have a very neat formula. So equal to d, if d equal to 1 mod 4, or equal to 4d equal to d 2 or 3 mod 4. So now associated with this quadratic extension, there is the quadratic characters given by the Legendre symbol delta over a, where delta over a here exactly is a Kronecker symbol. So it's a well-known fact that chi delta here is a primitive quadratic character, a conductor d, where d is the absolute value of deltas. So this Kronecker symbol here actually have meaning. So let's say the case where a is the prime numbers. So delta over p tell you whether the prime p is split, ramified, or unramified, or inert in the extension q adjoint root of d over q. So it have a very, very nice interpretation like that. And so the word quadratic here means that when you square it, you get 0, 1, or -1. You get 0, 1. So the value of this character is real. So it will be 0, -1, and 1. And in fact, there is a theorem saying that if you have a real characters, it have to be of this form. So basically, this Kronecker here, Kronecker symbol here, give you all possible real characters, degree characters. And then, so an object associated with any degree characters is L functions, which is given by this infinite series. We take the sum chi of n over n to the power s, where n is from 1 to infinities. So this series here is convergence as long as the real part of s is bigger than 0. So chi is not trivial. So it's convergent as long as the real part of s is bigger than 0, and it absolutely convergent if the real part of s is bigger than 1. And at s equal to 1, it has a very nice integral formula. So the value of the L function at 1 is given by the integral from 0 to 1 of a polynomial f delta here, divided by the factor x times 1 minus x to the power d. And the polynomial is given by this formula. So delta over a times x to the power a, where a running from 1 to d minus 1. And then, so our interest in this polynomial comes from the fact that at the beginning, a long time ago, 1.5 years, or 2 years ago, we want to find an elementary way to evaluate this integral. So, and then this polynomial just came out in the study. Now, so we give a name for this polynomial. So the polynomial f delta x here, you can index it by the character as well. So given by the sum a from 1 to d minus 1 of delta over a, x to the power a. This one we call the generalized Fekete polynomial associated with chi deltas or deltas. So what it means here is that the quadratic character here is determined by delta. So we can index it either by deltas or we can index it by the character chi deltas. So this definition here actually works for any character. So it doesn't have to be quadratic. But our talk will focus on the case of quadratic, like we explain in a second why that's important for us. So now I want to say a few words about history. So the KD equal to delta, where the conductor is a prime number. This one was first studied by Fekete. And so that's why we have the names. And he observed in a very interesting observation is that if this polynomial have no real root on the interval from 0 to 1, then the L function does not vanish for any s equal to 0 on the interval from 0 to 1. So in other words, if f have no real root, then he showed that there is no zero zeros of the L functions. So zero zero problem is a famous problem in number theories. And then he made the conjecture that the polynomial have no real root on 0, 1. So that's this conjecture turned out to be wrong. So I made the same mistake about that. So when I first studied this problem, I plot the figure for the Fekete polynomial for small p, I think up to p to 41, and I observed that it never touched the real light. So, and I asked the question whether it's true that the polynomial have no real root at all. And then one of my collaborators, he found the reference. So he found an article by Fekete, and he said that, oh, this polynomial have been studied before. And then he have a name. So we started to working on the problems. And to our surprise, there are a lot of work on Fekete polynomials. So for example, it has been studied the complex root of these polynomials or its extreme properties, but there are very few. In fact, there are none studies on the arithmetic properties of this polynomial. So we started to work on that to see what we can say about it. So one important tool that we have for this project is that we have computers. I think people don't have computers a long time ago. That's maybe one reason why no one studied, but we have computers. So we generate a ton of examples, ton of data, and we look at the data, see what we can see from the patterns. And in fact, there are patterns, and I will explain some of the patterns in my talk. That is an exciting part of the project. So I want to give some examples about the factorization of these polynomials. So let's phi n to be the n cyclotomic polynomial. So it's a product where it's a polynomial where all the roots are primitive n root of unities. And so let's take the k delta is equal to -3 times 5. So here we only consider the k delta is composite because the k delta prime is easy. So in this case, you see that the polynomial have the following factorizations. It has 5 factors. First of all, it has obvious factor x, and then you have phi 1, and then you have phi 3, it has phi 5. So you can see that it corresponding to the divisor of delta. So that's an important fact. So, and then finally, there is a last one, which is a reducible polynomial of degree 6. And then for delta equal to 3 times 7, we have the same pattern. So we have x, but now phi 1 is happen with square. Phi 2 happen. Phi 3 also corresponding to divisor of delta, and we have phi 7. So in this case, and then there's a last one, polynomial of degree 8, which is irreducible. So that is a factorization of f delta where delta equal to 21. And then finally, I want to give an example where delta is actually even. So the previous one, case where delta on odd. So in this case, f delta have this factorization into phi 1, but the polynomial is actually polynomial in x squared. And same thing, phi 2, but with the variable x squared, and phi 11 with the variable x squared. And finally, there is a polynomial in x squared, where this polynomial is given by this. So it's an irreducible polynomial. So what we observe here is that if chi even, then chi delta equal to 0. So as a consequence, the polynomial f delta over x is a polynomial in x squared. So in other words, it contains more information. So it can contain redundant information. So we make the following modifications. So we define the modified Fekete polynomials to be the polynomial where basically it's a polynomial in x squared. And concretely, it's given by this formula here. So the sum from a from 0 to d over 2 minus 1, but then you only take into account the odd number. So delta over 2a plus 1. So for example, if you follow this one, it says that if delta equal to 4 times 11 with 44, then the f tilde have this factorization. So you have a phi 1, phi 2, phi 11, and finally you have f deltas, where f delta is a polynomial that I just mentioned above, and it's reducible. So now, so the observation that I think the example that I just showed that show us that we have the following observations. So if any divisor of d and any not equal to d, then phi n is a factor of the Fekete polynomials, right? And so now we're trying to, so we make this observation after some by looking at the big set of data. So it's not obvious, but just look at that, it's not obvious. But you take a look at a big set of data, so you have this feeling that it's true. And then so we try to prove that. So the way we observe this is the following. It turns out that this is related to the classical theory of Gauss sum. So we now recall. So if b is an integer, I fix a primitive d root of unities. The Gauss sum, where I have two variables, so b and chi, you define as follows. You take the sum from a from 1 to d minus 1, chi of a, and you multiply by zeta d to the power ab. So in other words, it is the evaluation of the Fekete polynomial of zeta d to the power b. And then there is the fundamental properties of the Gauss sum, which basically say that you can take the b out and calculate the Gauss sum at 1. That's enough. So a direct consequence of this one is that if the b and d are not relatively prime, then by definition, chi of b equal to 0. So in other words, the evaluation of zeta d to the power b of f of Fekete polynomial have to be 0. So here we take a look at that. So if b and d are not relatively prime, then zeta d to the power b is a d root of unity, but it's not primitive. So it could be, it's not primitives. That's important. So in other words, it says that if n is a divisor of d, and then n is not equal to d, then the Fekete polynomial vanishes at zeta n. So in the case where n equal to d, then in fact, the theory of Gauss sum say that the absolute value of g of 1 chi is equal to square root of delta, so it's non-vanished. So in other words, if zeta d will not be a root of this polynomial, but zeta n for any n is a divisor of d, and strictly smaller than d will be a zeros of this. So now this raises the following questions, I think quite natural. So let n to be a positive integers. What is the multiplicity of zeta n as a root of these polynomials? So now we have some remark about this one. So first of all, the first remark here is that in the above questions, we do not require that n to be a divisor of these. So we'll see in a moment some example where that could happen. And we will see that the multiplicity is not always one. So this is a surprising fact. And then so we will write Rn, R delta phi n to be the multiplicity of phi n in the Fekete polynomials. And finally, so in this talk, I will only consider the case where delta is odd. Delta even is due to time constraint. I probably don't have enough time to talk about delta even, but it also have some interesting phenomena. So I think that would be kind of the introduction part of my talk. I want to pause a moment if people have any questions for clarification before I go into details. Okay, so no questions. So let me move on. Okay, so now I'm going to talk about an easy statement from the papers, which is a multiplicity of phi1 and phi2. So we call that phi1 is x minus 1 or phi2 is x plus 1. So the question is, what is the multiplicity of 1 and negative 1 as a root of this polynomial? And the proposition is followed. The multiplicity of phi1 will be 1 if delta is more than 0. It will be 2 if delta bigger than 0. And similarly, the multiplicity of phi2 will be 0 if delta is less than 0. And it will be 1 if delta is bigger than 0. So I will give a proof of this one. It's a little bit technical, but it's a prototype of our proof for basically all other propositions. And it is based on the following strategies. So first of all, let's take a look at the first proposition. We talk about the multiplicity of 1, right? So we compute f delta of 1. It's the sum of all the on character chi a, where a from 1 to d minus 1. And we know that this sum is 0. So in order to study the multiplicity, what we have to do, we need to consider the higher order derivative. So we basically take the derivative until it non-vanish. So that tells you the multiplicity. And the strategy for basically on the proof is followed. We connect the following three objects. So we connect the higher derivative of the Fekete polynomials to Bernoulli numbers. And then we connect Bernoulli number to special value F functions. And when we are at the length of special value F function, we can say whether it vanishes or it doesn't vanish. And then we go back to the derivative of Fekete polynomial. And I will explain the proof in a moment. Before that, I will explain what it means to be higher derivative of Fekete polynomials. Now I will explain, maybe recall the Bernoulli numbers and special value F function and their connections. These are classical topics. So if I have chi to be a primitive declared characters of conductor F, the generalized Bernoulli numbers are given by this very complicated infinite series. You look at it. But in practice, there is a recursive relation between B and chi. In fact, we can write some computer code to compute it. It's very efficient. So this definition, in my opinion, is the definition, but it's hard to compute in practice. But there is another recursive relations that much easier to implement on computers. And then there is recall that the L function that I mentioned earlier, given by this infinite sums. And then it turns out that there is a very neat formula of the special value of L functions and the Bernoulli number. So the value of the L function at 1 minus n chi is given by the value negative of bn chi over n. So here, of course, we need to take the analytic continuations of the L functions in order to make sense of these negative values. And then furthermore, so this L function here, it has a functional equation. So there is a connection between the value at s and the value 1 minus s. And by that functional equation, we can say something about the vanishing or non-vanishing of the Bernoulli numbers. So So I define delta of chi to be 0 if the character is even. So in other words, chi of -1 is 1, and delta chi will be 1 if the character is odd. So that means chi of -1 equal to -1. So this says that the Bernoulli number does not vanish if n is congruent to delta chi mod 2, and it vanishes if n is not congruent to delta chi mod 2. So this theorem I took from Iwasawa's book on I think lecture on periodic F functions, and he have a kind of interesting comment that so the number B1 chi it have simple form of sum of chi of A times A, and he say that he doesn't know any elementary proof for the fact that it's not zeros. So the only proof he knows is using these F functions. Okay, so now I go back to the main proof, explain the idea of the proof. So first of all, I need to talk about the size of the character. So we know that in this case, delta chi will be equal to 0 if delta is positive. So it is an even character if delta bigger than 0, and it is odd characters if delta less than 0. And we already saw that f delta of 1 equal to 1. So now we consider higher derivatives. So the first derivative is given by this formula, the sum of chi A times A, and is equal to d times the first Bernoulli numbers. And this will be 0 by the previous theorem if delta is bigger than 0. But it's not 0 if delta is less than 0. So in the case where the character is odd, we already know the multiplicity which is 1. But for the case where the character is even, we need to take second derivative. And for the second derivative, we have this formula, and it turns out that it equal to d times the second Bernoulli numbers. And we know that it's not 0. So in other words, we just prove that the multiplicity of phi1 is 1 if delta is less than 0, and it will be equal to 2 if delta is bigger than 0. So yeah, so that is a prototype, the proof for the multiplicity of phi1. For phi2, the proof is almost the same. And in fact, what I want to say here is that the proof here will actually work for any characters. It doesn't have to be quadratic. But as I said earlier, the focus of the talk will be on quadratic characters. So, okay, so I want to talk about the next one. So now I want to talk on some special case where delta have a few prime numbers. So the first case I consider will be the case delta is 3p. So p is a number count to 3 mod 4 to make sure that delta is count to 1 mod 4. So delta is 3 times 7. We see that it have a factor of phi1, we know how to explain that. Phi2, we know how to explain that. Phi3 is appear, but we don't know the multiplicity, but here is 1, and we know phi7. So this case have kind of a normal case, so you don't see anything unexpected. But this case, with delta is 3 times 11, this case is a new phenomenon. So you have phi1 square, this is expected. Phi2, we know how to explain that. But phi6, so 6 is not a divisor of delta. So this is a new phenomenon. You have it's exceptional zeros. And phi3, so phi3 expected, but now the multiplicity is 2, so it's also a new phenomenon. And phi11, so it's irregular, so nothing happened at 11. And the same thing happened for delta 3 times 19. So in this case, it behaves almost the same thing as the case where delta is 3 times 7. So now I give a table for further values of p. So for p in the range from 7 to 43, the multiplicity of phi3 and phi6 are given by these formulas, are given by these tables. So maybe I want to pause a moment if people want to make some predictions about the multiplicity here. So I will pause a moment. So you have, if you find any patterns, so please speak out. Otherwise, we continue.
Multiplicity for phi6 is 1 less than phi3.
Yes, this is always the case, yes.
So when the prime is 1 mod 3 and 2 mod 3, it's different?
Exactly. So that is exactly the pattern. So that we observe and prove the theorem that we basically generate a big list of data. We look at the tables, see what happened, and then we try to prove that. Yeah, so that exactly the observation. So the multiplicity depend on P mod 3. So for example, for phi3, the multiplicity in 1 is 1 mod 3, can be 2, it be 2 mod 3. And the same thing for phi6, but less than 1. Yeah, Professor Payman have said. And then we define the Fekete polynomial. So it's quite easy to show that the multiplicity of phi b is 1. So this comes from a general fact that when the number n here, phi n here, when n is big relatively to delta, then the multiplicity is over 1. And so we define the Fekete polynomials by basically we take the generalized Fekete polynomials and we factor out all the cyclotomic factors. So because of the fact the multiplicity different in the case with p is 2 mod 3 or 1 mod 3, so you see that the factor here are different. So that's the definition of the Fekete polynomials. And the second observation that we made is that the following. So f deltas turned out to be a reciprocal polynomial of even degrees. So let me go back to here. So you take a look at this, for example. So the coefficient of x to the power 8 is the same thing as the coefficient of x to the power 0. The coefficient of x to the power 7 is the same thing as the coefficient of x. The coefficient of x to the power 6 is the same thing as the coefficient of x squared. And the same thing happened with other cases. So in other words, the coefficient is symmetric with respect to the middle terms. It will have some consequence, and we'll see later. And then I talk a little bit about the case where delta is to negative 3p. So in this case, it turns out there are no exceptional zeros, and also the multiplicity is expected. So the Fekete polynomial have a very neat formula like this. So we define, take the generalized Fekete polynomials and we divide by the factors. And again, we observe that is the reciprocal polynomial of degree, even degrees. That's important. Okay, so now to go to the next part of the talk, which is the Galois theory for generalized Fekete polynomials. So because f is reciprocal polynomial of even degrees, we can write as a polynomial of x plus 1 over x. So the polynomial g here is called the trace polynomial of f. Right, so already we see that the Galois group of f cannot be true. We have some restrictions, that's what I want to say. So now I explain what the restriction is. So the Galois group of g deltas have to be a subgroup of Sn, H delta, where H delta is the degree of g delta. So we act on the set of roots and it permutes the roots. So that's why it's a subgroup of S of H delta. And the Galois group of F delta fit into the following exact sequence. So first of all, we have the projections with the Galois group of g deltas. And the kernel of this one is a Galois group of Q of F deltas over Q of G deltas. But by definition, the root of F is obtained from the root of G by solving the equation x plus 1 over x equal to the root. So naturally, this first Galois group here have to be a subgroup of D mod 2 to the power H deltas. So in total, we see that the Galois group of F deltas there's a typo, so it should be Q here. So this is a subgroup of the semi-direct product of this semi-direct product, and the action here of S, the symmetric group, basically it permeates the element in this D mod 2 here. And furthermore, this group here is also a natural subgroup of S2H delta, because the Galois group F also acts on the root. But you can imagine that this semi-direct product group here is much smaller than these big groups. So we already see that there's some big restriction on the Galois group of F. Now, so I want to talk about the previous work on this. So in the case where delta is to P, we show in the previous work that for P is less than 1000, the Galois group of F is exactly the semi-direct product. And the Galois group of G is the symmetric groups. So in other words, both in the case where delta is the prime numbers, the Galois group F deltas and G deltas are both as large as possible. So it's maximal. So here is a amusing corollary of this fact. That is a consequence of this one, is that for P less than 1000, both of these polynomials are reducible. And so that is one method to prove they are reducible. Okay, so now I want to talk about how we find out that these polynomials are maximal. So the method is, at the beginning, the method is very brute force. So we compute the degrees and it turned out to be maximal, but it's only work for small p. I think we put the polynomial in magma, but it stopped after p equal to 43 or something. So we submitted the paper and the editor said that you need more evidence. And then we work harder to find more evidence. So, and then I remember that when I took a course in Galois theory, there's a very nice criterion to say that when the Galois group of polynomials would be Sn. So it comes from the following observation. So if you have a subgroup of Sn, which contain an n cycle, an n-1 cycle, and a 2 cycle, then it have to be everything. So in other words, if we translate this one into the context of a polynomial with z, it says that if g is reducible, so this says that the Galois group have an n cycles, and it have the factorizations into a linear term times a irreducible polynomial degree n-1. It says that it have n-1 cycles, and the last condition says that it have 2 cycles. So by studying the factorization of this polynomial modulo prime numbers, we can conclude that the Galois group of G is Sn. That is the method. And similarly, there is also criteria we due to Davis, Duke, and Sun. So they study a random reciprocal polynomial, and they prove that most of the time they have the maximal Galois groups. So I probably will not go into detail about this one, but it's also come from group theory. So you have a subgroup of semi-direct product which contains certain elements, 4 type elements, and it have to be everything. So this that's what we use in the previous work. Now, so we try to apply the same criteria for p where delta have a few prime factors, and it worked for p less than 500 most cases, except in the case where delta is to -3p. So in this case, we were unable to find the prime. The first prime here, where f is reducible. And so what we did was we use magma. So for small p, we use magma. What happened is that the Galois group is not the whole, the semi-direct product, but in fact it's a proper subgroup. And we work really hard to explain the phenomena. And it turns out that in this case, there is a hidden, or I would say an exceptional symmetries that we didn't catch. And the hidden symmetry is the following. So in the case where delta is to -3p, then the discriminant of this polynomial is a perfect square, if and only p equal to 5 mod 8. So it's not a perfect square when p equal to 1 mod 8, but it's a perfect square when p equal to 5 mod 8. So this will put some restriction on the type of Galois group of f deltas. I will explain in a second. So here I want to add a few words about the discrimination of f deltas here. So you may ask how we compute the discriminant of f deltas, given that it's kind of complicated polynomials. So it turns out that when f is a reciprocal polynomial, the discriminant of f can be computed in terms of the discriminant of g. In fact, it's some factor times the discrimination of g squared. So we just need to compute those factors, and those factors are very easily computable. And in this particular case, those factors are related to special value F functions. Okay. So now this comes from the following observations. So I mentioned earlier, we can consider the semi-direct product Z mod 2 times n. Semi-direct with Sn is a subgroup of Fn. And so on Sn, you have a psi map. The psi map, just tell you is it even or odd permutations. And it turns out that if you take sigma to be the map, where you take the tuple A1, A2 up to AN sigma, you forget about the sigma, you just take the sum of AI, then this is the commutative diagrams. So what happened here is that if this combination of delta is a perfect square, then the Galois group of F deltas, it have to be contained in the even permutation subgroup. And in particular, it have to belong to the, because of the commutative diagram, it belongs to the kernel of these map deltas. And we can note that because by its definitions, the kernel of delta could be identified as a semi-direct product of the kernel of sigma star, sigma prime. Okay, sigma prime is just a summation map. You take the AI, you send it to the sum of AI. So in other words, when the discrimination is a perfect square, you cannot get the whole group, but you can possibly get the smaller subgroup. And so here is the amusing consequence of this fact. So in the case where discrimination of f is a perfect square, we expect that f's delta is reducible over z, but it have to be reducible over f cubed for all prime cubes. And the reason is very simple. If it is reducible mod q, then the graph group have contained a 2n cycle, but a 2n cycle is an odd cycle, it's an odd permutations. So it contradicts the fact that it have to be an even permutation. So for example, you go back to this. I don't know, I think we have an example here. Yeah, I will give an example later on where you have the case. So now in order to deal with that exceptional symmetries, we found the following lemmas. So if you have a subgroup of these semi-direct products, satisfy the following conditions. So the natural projection from H to Sn is surjective, and H contains a product of 2 cycles and another 4 cycles. And these 2 cycles are destroyed. Then the conclusion here is that H have to contain the subgroup, the kernel of sigma delta semi-direct product with Sn here. So that is our strategy to deal with the case where the discriminant of f is a perfect square. So we can translate this into a problem in about polynomials. It's simple. So that f is a polynomial, reciprocal polynomials of even degrees, and g the trace polynomials. So we assume that the discriminant of f is a perfect square. So it's contained, the Galois group is contained in the subgroup that I just mentioned. The Galois group of g is Sn. So in other words, the projection H from H to Sn is surjective. And there exists a prime number q such that f have this factorization. So it says that the Galois group f have the product of 2 cycles and 4 cycles. Then the conclusion is that the Galois group of f is exactly the subgroup kernel of sigma star semi-direct product with Sn. So here I think I have one example. So let's take this particular example where delta equal to 4 times 19. So in this case, we check that f, the discriminant of f delta is a perfect square. So we know that the Galois group of f deltas have to be a subgroup of this semi-direct product. And the Galois group of g delta is S8. So in order to compute the Galois group of g, we just do the previous criteria. So we contain an n cycle, n minus 1 cycle, and 2 cycles. And at the prime number q, we go to this number, it have these factorizations. So we say that the Galois group of f have a product of 2 cycles and 4 cycles. So we conclude that the Galois group of f deltas have to be exactly this subgroup. So this is a concrete demonstration of this one. And then I mentioned earlier, so this polynomial is reducible over z, but will be reducible over any prime number q. Okay. So now because we already proved the previous lemma, we feel that we might simplify the theorem of Davis, Tung, and Sun a little bit. So I'm going to explain some advantage of this approach. So it H will be a subgroup of the semi-direct product of z mod 2 over n, semi-direct product with Sn. And I assume that the natural projection map from H to Sn is surjective, and Hn just need to contain a 2 cycle. Then it have to be everything. So we can translate this one again into the problem about polynomials. We say the following. So if f is a monic reciprocal polynomial of even degrees, and g the trace polynomial of f, we assume that the Galois group of g is Sn, and there exists a prime number q such that when you factor f mod q is a product of quadratic polynomials, and Hx is a product of distinct reducible polynomial of odd degrees. So the conclusion here is that the Galois group of f is exactly this semi-direct product. So in some sense, this theorem is very similar to the theorem of Davis, Tung, and Sun. But in practice, it's much faster because the degree of G here is a half the degree of F. So when you take factorization mod Q, is more efficient. So that's why we're able to check the conjecture for larger primes. So from our numerical or experimental data, we made the following predictions. So that if delta have few primes, so in other words, delta belong to this set, it would be 4p, negative 4p, 3p, or negative 3p, and H delta to be the degree of G deltas. So if discrimination of delta is not a perfect square, then the graph group of F deltas is exactly the semi-direct product Z mod 2 to the power H delta, semi-direct product with S of H delta. But if it is a perfect square, then it will be the subgroup kernel of sigma star semi-direct product with the symmetric group on H delta letters. And we have been able to verify the conjecture for OOP less than 1,000. So I think that is a so I think that's the first part of the talk. I want to pause a moment if people have any question before I move to a completely new different topic.
Maybe I'll ask a question here. So here, if you, okay, so what if you look at, in the case that you look at, let's say 5p and minus 5p, do you have any conjectures that sort of, what sort of thing you might expect in general?
Yeah, so that's a great question. So in the case of 5p, I think in that case, probably don't have exceptional zero, it's just phi 5 and phi p. And the graph group should be follow these patterns. So in general, so the problem is still define what is F deltas, because in order to define F deltas, we need to know all of its cyclotomic factors, and what remain will be the Fekete polynomials. And I think that it's the same pattern here when it happens. So that is expectation for in general, but I don't have the data yet to say precisely. I'm still working on that. Yeah.
Okay, thank you.
Yeah, a great question. Thank you. Okay, so no questions. So I move to a completely different topic. We will finish last month or so. Okay, so now I want to follow this circle of ideas. So in our lab, we study nonlinear dynamics. So a very important topic is spectral graph theories. And the many kind of graphs, we want to have explicit spectrum. So we can do have analytical solution for some problem in computational neuroscience. So now I want to explain this circle of ideas to construct some new family of graphs, and I will give some classifications. So let chi to be the quadratic characters associated with chi with delta that I mentioned earlier. So the Paley graph is a graph with the following data. The vertices of p deltas is a set from 0, 1 to d minus 1. And we say that two vertices are connected if you take the evaluation of the character of the different u minus v is equal to 1. So in the case where delta is a prime number, this is exactly the Paley graphs, classical Paley graphs. Because the classical Paley graph says that two vertices are connected if the difference is a square. So that's what happened here. And then because the connection in p deltas is determined by the different v minus u modulo d, so p delta is in fact a circular graph with respect to the cyclic groups. So it's, in other words, some people call it the Paley graphs, and the generating set is the kernel of the map chi. But anyway, so its eigensymmetric is very simple. It's generated by the first row vectors. And this first row vector is given by this formula. So to make sense of this one, you can imagine that if chi of A equal to 0, then this is 0. So there are no loops. But if chi of A negative 1, let's say that is 0. So there are also no connections. It's 1 if chi of A equal to 1. That's the only case. So that is why this one represents the connections of the matrix. So here is the corollary of this one. You take the sum of all elements in these vectors, you get phi d over 2. So in other words, the degree of this of this graph is phi d over 2. So now we want to compute the spectral of this graph. And the spectral of this one by the circular diagonalization theorem is given by this sum. So you take the generating vectors and you multiply by the appropriate n root d root of unities. So you have this formula, but you can break it in two terms. The first term is 1/2 of chi a times omega to the power a. The second is omega a squared times omega to the power a. The first term here is actually the Gauss sum I mentioned earlier. This one is basically the sum of root of unities. So both of some are known for quadratic characters. So we can simplify it. So if I write AB for the multiset AA, where A appears B times, then the spectrum of this polynomial of this graph is given by this following multiset. So for H divisor B, where D is strictly less than D, you have phi D over phi capital D over phi D times the Mobius function of D, and this happens with multiplicity phi D times. And then you have two actual eigenvalues, given by square root of D plus mu D, and then this happens with multiplicity phi D over 2, and then the second one is coming conjugate pair with the first one, but the multiplicity phi D over 2. So this gives you a complete classification of the spectrum of this one. So in the case where P is a prime numbers, this we cover the classical calculation of Paley on the spectrum of Paley graphs. So now I want to talk about the following question: which Paley graph are Germanusians? The Germanusian is some kind of expanded graph. It's very important in practice. So we want to classify, which Paley graphs are Germanusians. Before I do so, I need to recall the definition of Germanusian graphs. So if I have a connected regular graph on n vertices, so regular means that each node is connected to others nodes. And we know that because the graph is undirected, so its eigenvalues are real, so I can order them in the decreasing orders. And then I take lambda g to be the maximum of all eigenvalues, where lambda I is not R or negative R. So the case negative R could happen if the graph is a bipartite graph. So we could happen in the Paley graph because when D is even, we can partition the vertex into the odd vertex and even vertex. So G is a bipartite graph. So in that case, negative R could be an eigenvalues, but we don't care about that. So we take the maximum of all eigenvalue, we have absolutely strictly smaller than R. And so we call that the graph G, the Germanusian graph. If lambda G satisfies the following inequalities, that is a lambda G here, be at most 2 times the square root of R minus 1. And so here's a complete classification of Paley graph with Germanusians. So from the spatial calculation, we know that the D here, this conductor cannot have too many prime factors. And in fact, you can see that it can have at most 3 prime factors. And furthermore, by the restriction on the being Ramanusians, we have some relation between the prime factors. So this is very long, but basically there's 6 cases. So the first case is that D equal to 4P, where P is a prime number con 3 mod 4. Or it could be 8P, where P also an odd prime numbers. Here the case P equal to 1 also Gauss. And it could be the product 4 times P1, P2, where P1, P2 are distinct primes, and it satisfies these inequalities. And it could be 8 times P1, P2, which satisfy this inequality. And there is a classical case where D is just a prime numbers, and this also work. And finally, it could be the product of 2 prime numbers, and it satisfies these inequalities. So what is the final thing I want to say that for all the condition here, for example, condition 3 here, condition 4 here, condition 6 here, by the prime number theorem, there exist infinite many pairs P1, P2 that satisfy these inequalities. So in other words, we have an infinitely new family of Germanusian graphs coming from the Paley graphs. So I think that's all I want to say. Probably we stop here and thank you for the attention.